this video on reflection. Now, what's the learning objectives? Well, this is the overall what I'm going to try and get through the next few videos. But this one particularly, you're going to understand light waves are transverse waves which can be reflected. Okay, and in more detail, we're going to use the laws of reflection, which means the angle of incidence, we'll come across in a moment, equals the angle of reflection. And in particular, we're going to construct ray diagrams to illustrate the formation of a virtual image in a plane mirror. Let's start first of all looking at the basic components, shall we? Now, in any ray diagram like this one here, you're going to have what's called a plane or flat mirror. This side here represents the front of the mirror, this side here represents the back of the mirror. Now, we've also got something very special called a normal line. Now, a normal line is a line that is at right angles. If I can draw a right angle there. Pretty good, isn't it? A normal line is at right angles to the mirror. It's an imaginary line, doesn't really exist, but it helps us in our drawing of the ray diagram. Okay, what else we got? Well, coming in, we're going to have what's called an instant ray. Now, this is the ray that's coming in towards the mirror from an object. So object could be down here somewhere, and the instant ray is a ray of light that will come in and it's going to strike the mirror at this point here. This angle here between the instant ray and the normal is called the instant angle. Now, this ray coming off here, this ray is being reflected, so it's referred to as the reflected ray. Not surprising, is it? And which means this angle here has got to be the reflected angle. Okay, so some important bits there. We've got instant ray, okay, we've got instant angle, we've got reflected angle, and we've reflected ray. And don't forget, please, the normal as well. So those are the basic components in our diagram here. Now, there's a couple of very, very important rules you've got to learn about in doing this, and that's as follows. First of all, always use a ruler to draw light rays. So we're drawing the instant ray and the reflected ray. Don't be like me with these horrible wiggly lines. You should use a ruler to draw light rays. Why? Well, basically, because light travels in straight lines. Okay, so always use a ruler when drawing these. Now, the other thing you must have, and examiners be looking for this, is you've got to have arrows to show the direction in which the light is travelling. So see here, I've got an arrow here. Okay, I've got an arrow here. Now, these are showing us in which direction light is travelling, and that is so important, something that the examiner will be looking out for. So that's a basic diagram. And if you're doing a practical of this, what you would do, you'd shine a number of, you can't really see the arrows. The arrows are there. Okay, put the arrows on there like this. Okay, what you would do in this sort of experiment, you'd shine lots and lots of instant rays, and you record the reflected rays coming off. So these instant rays, these reflected rays, and you measure the angles of these. And what you'd find is two laws of reflection. First of all, it says that the instant angle, that's this one here, okay, in a plane mirror, the instant angle always is always equal. Sorry, start again. That's bad, isn't it? The instant angle here is always equal to the reflected angle. That's that one there. Okay. Now the second one says the instant ray, the reflected ray, and the normal all lie in the same plane. Now, what that means is that you can actually draw these on a flat piece of paper. So don't get too hung up about this same plane bit here. What it means is you can draw all these on the same bit of paper. Okay, so those are the basic rules there. Reflection, the angle of incidence is always equal to the angle of reflection, and the instant ray, the reflected ray, and the normal always lie in the same plane. Let's look now at the image in a plane mirror. Now, over here we've got an object. Now the object is so we're looking at, and here's our eye down here. Okay. Now if you look, here's the object. Now there are obviously thousands of light rays coming off here. We can just take two. So two of these light rays, follow them down. They get reflected off the mirror like this. Now, of course, we know about the laws that govern light reflecting the plane mirror. We can actually trace those rays back. So if we take the mirror away, okay, we can trace these lines back here, and we get the position of the virtual image. Now, these lines here do not actually exist. They are virtual lines, but they're dotted lines to show construction of the virtual image. Okay, so that shows us there the position of our image. Now, the key thing is the image, okay, the image in the mirror looks exactly the same, but it's what we call laterally inverted. Now, you may notice this if you're looking in the mirror at your own reflection, that left seems right and right seems left. That's what we call lateral inversion. So lateral inversion means it looks back to front. So here, there's the microphone there in our singer's hand, and over here it looks opposite, doesn't it? Well, that's what we call lateral inversion. So in a image in a plane mirror, we get lateral inversion, and we draw these lines here to show the position of the virtual. It's virtual. When we say virtual, it means it doesn't really exist. Okay, we think it does, but it doesn't. This is the sort of thing that drives your cat mad. When your cat's looking at this image in a mirror and it can't really understand. There seems to be a cat over here, but it can't find it because it's virtual. Now we use this inversion in some really important ways. And one of those is when we are being followed by an ambulance. Now here's an ambulance over here. You can see the ambulance. That word there is written back to front. Why is it written back to front? Well, the very good reason is that when you look at it in your rear view mirror, what you see is the word ambulance the right way around, because it's been laterally inverted. So it's a very, very important use there of lateral inversion. Right, now let's think how we're going to find the position of this image in a plane mirror in more detail. Now we need to have for this a plain bit of paper. We also need to have a pin, and we also need to have a mirror. So we put the mirror upright on our plain piece of paper, we put a pin in front of the mirror, and we mark the position of both using a pencil. Okay. Then what we do is we get down. So we have to get down now at the same level of the mirror. And what you do, use a ruler. Now use this like a little guide or a little target. You look along the edge of this ruler here, so you can see the image of the pin. So you're looking along the edge of this ruler here. You can see over here the image of the pin. Okay, there's an image there. Look on the edge. So you draw a line to mark the position. We then do, you go to the other side of the pin, do exactly the same thing, and here you repeat with the ruler in different position. You look along the edge, you have to get right down here, eye level with this, and you draw another ray coming in here. Now, if we then take away the ruler and the mirror, and we join these two lines up here we've got the virtual position, okay, of the image. That's where we perceive the image to be coming from. Now we can test this by actually getting a real pin and putting the real pin in the position where we think the virtual image was. Now, wherever you look from, you can look from here, you can look from there, okay, the second pin here should always stay in line with the mirror image. So these two here should be lined up. Now what we have for that is a term no parallax. So test position by putting the second pin exactly where the image was marked. The second pin should stay in line with the mirror image wherever you view it from. And there's a term here called no parallax, something worth thinking about. Now what are the rules for mirror image? First of all, the image is the same size as the object. So this image here appears to be the same size as the object here. Secondly, the image is as far behind the mirror as the object is in front. So this distance here is the same as this distance here. Okay, so those are the two rules for mirror images. Right, so let's just check. What have we done? We've been looking in this video at the term reflection. We've been able to use the laws of reflection to show that the angle of incidence always equals the angle of reflection. And lastly, we can now construct Venn diagrams to illustrate the formation of a virtual image in a plane mirror. Now I think we've done that, so we can tick that off. We've done all three of those things there. We tick all those off. So that's the end of this little video on reflection. Thank you for watching. Thank you for listening. Please go back over it again to check you understand everything I've been talking about. But I look forward to seeing you again very, very soon. Bye-bye for now.